I'm back. So,
Okay, yeah, Bhaskaran was saying hello to you.
oh, Bhaskaran, hi, how are you? Bhaskaran, can you hear me?
He was.
I can hear you. I can hear you.
Yes,
Yeah. How are you?
I'm okay. Where are you?
I'm at Chennai.
You're at Chennai. I see. Okay.
See, I was planning to go to Canada. Then this lockdown came, and I'm locked down here.
Okay. I'm glad you are here, so I can hear you and you can criticize all my lecture. Give me some. So this is first time I'm giving a talk at all in this
Oh,
virtual
wonderful,
class.
wonderful, wonderful. Yeah, yeah.
Also on this subject.
Bonu, you remember where we met last? In Gopalpuram.
Yeah, that was
Yeah,
right.
yeah. Wonderful. Yeah.
Well, let's hope we meet again sometime soon.
Sure, sure. Yeah, I'm sure.
Okay, let me introduce Professor Mahanti, and then we'll get going. So today, our speaker is Professor Suvendra Mahanti from Physics Department at Michigan State University. The title of the talk is Amplitude Modes in Quantum Condensed Systems. Are they Higgs modes? Let me say a few words about Professor Mahanti. He is a theoretical condensed matter physicist. He did his BSc from Utkal University in 1961, MSc from Allahabad University in 1963, where he was a gold medalist, and did his PhD from UC Riverside in 1968. When he was only 23 years old, by the way. He was at Bell Labs as a member of the technical staff from 68 to 70, and has been at Michigan State since 70, and he's currently an emeritus. He's a fellow of the American Physical Society, and he has co-authored more than 290 journal papers. He was on the editorial board of several journals, and for the last several years, he has focused on understanding electronic and structural properties of complex systems, narrowband gap semiconductors for thermoelectrics and topological insulators, and magnetism in strongly correlated systems. He has been a PI or a co-PI of several large projects funded by DARPA, ONR, and other agencies. He was one of the leading co-PIs of the Center for Revolutionary Materials for Solid-State Energy Conversion, an Energy Frontier Research Center funded by DOE. Let me take just a few seconds maybe to add that he was my postdoctoral supervisor at Michigan State from 1990 to 1993. And those 3 years were probably the most supercharged years of physics that I had with him. And pretty much everything I know, I can blame it on him. So with that introduction, let me give it over to him for getting started.
So can I start now?
Yes, you're ready to go.
Okay, hello everybody. I can't see any of you. Hopefully some of you are my friends whom I have met over years. And when Surajit wanted me to just listen to a part of this series, and here sitting at home, just doing things, not anything exciting, can't go to the department. So I was very excited about joining his lectures. Then he tracked me to give a talk. So I've never given a talk virtually. So I'm sitting in a room, looking at my computer screen and talking like a mad person to the screen. I hope you will bear with me. And this is something which I have been doing on the side. I retired almost 10 years back, 8 years back. But one of my very close experimentalist friends, and one of my very close theorist friends, Kaplan, passed away. So he and I used to work on magnetism. And this experimentalist used to come and talk to me. And he used to come and show me the data. And I got interested. And I'm going to talk about something which I learned over the last year or two, maybe 3. And I don't understand a lot. But I want to tell you about what I have understood. And let's see how it goes. One thing I was also reading some article about during the time of COVID, when you're a professor, a student, or a counselor, it becomes little bit more personal. So, I'm also learning, and there will be some students and some experts in the field. Hopefully students will understand. So my lack of deeper understanding and so on, and the experts will help me to understand. So this is like a mutual learning process. So I'm going to talk about something called amplitude modes, which is very well known. And so there has been a question whether they're Higgs modes, which I did not know. When we wrote a paper, I'll tell you later, we wrote a Higgs mode and the referee said it's not Higgs and so on. So I went back and started to learn a little bit. And what I've learned, I'm going to tell you. And I acknowledge my experimentalist friend K here, K, and Chandravarma is my old friend. I asked him a few questions, and Matsumoto is a theorist with whom we worked, and he did most of the calculations. And I also thank Surajit for asking me to come here. Okay, so let me quickly introduce. You know a lot about symmetry, a lot of you know, and tell you about spontaneous symmetry breaking very quickly. Then I'll tell you about the order parameter and Landau-Ginzburg potential energy or free energy, whatever you call it, and define the amplitude and phase. Then I'll talk about phase and amplitude modes, and the amplitudes are sort of synonymously called Higgs modes, and you'll see that they are under certain conditions they will be called, and I'll tell you when. Then I'll give two examples. One basically depending on following the work of Chandravarma and Pecker, their review article. I followed their paper, read not all of them, but beginning part of their paper. And then I'll tell you about quantum spins, which we worked a little bit. Sorry. Okay, now, as you know, symmetry, of course, is a very beautiful thing, unifying concepts in physics. Most symmetric stuffs are beautiful, and like to have Hamiltonians, Lagrangian symmetry, we can use group theory and so on. But however, symmetry, perfect symmetry is not very exciting. Symmetry breaking gives you a lot of more exciting stuff. And one of the particular type of symmetry breaking is spontaneous symmetry breaking. Of course, symmetry breaking, as you can see, you take a sphere, make a cube tetragon, the symmetry changes. Properties of materials change with the change in symmetry. But the spontaneous symmetry, of course, is something more deeper, and a system spontaneously goes from one type of state to another type of state. The ground state, for example, doesn't have the same symmetry as the Hamiltonian. So symmetry is broken. And what is interesting, this symmetry broken state can have long range order, does have long range order. One defines an order parameter in phase transitions, as you know, going from para to ferro. There is a magnetization, or a para to antiferro. There is a staggered magnetization, normal to superconductor, superconducting order parameter, and so on. And what is interesting is that the broken symmetry phase, or the system with long range order, that new state has a lot of exciting properties. It has rigidity. And in fact, the great famous Anderson's, I think, old paper or book I read is rigidity in collective states. Anderson's book, I think. I don't remember. Then, of course, you have collective states of the matter, magnons in ferromagnets, spinons, of course, are different. Phonons, for example, is a good example. There are also emergence of new particles and excitations in the broken symmetry state, and which will be addressing something here. Okay, now just to briefly summarize, spontaneous, I'm talking about continuous symmetry breaking. That means, let's say, rotational symmetry at the high symmetry phase, and it breaks to with a certain direction become preferred, like a ferromagnet. So what we have, there's just a summary that in the broken symmetry phase, we have what is called as Nambu, Goldstone, Bogoliubov, many names. I just put them all three excitations. They are the coherent phase fluctuations of the order parameter. Order parameter has some value like magnetization, and it has an amplitude and a phase, and the phase fluctuations like the rotations of the magnetic moment coherently across this system has an energy, and that energy goes to zero, or what we call gapless modes. Magnons in ferro and antiferro magnets. And so there, of course, in magnets, for example, easy to understand the ferro one, rotational symmetry is broken. Antiferros are a little more tricky, we'll come back later. And the example I'm going to do today also is superconductors, where, of course, when you go to the condensed phase, you form pairs and the gauge symmetry is broken. And of course, there are a lot of exciting things happen. And recently, I read very nice paper, 2 articles, in fact, by Bhaskaran, who is here. Anderson was one of the great ideas he gave, that the symmetry breaking in superconductors gives rise to bosons. And they, of course, because they are phase fluctuations in a charged system, have currents, they couple to the electromagnetic field, and they become massive. And that's the whole idea of Anderson mechanism, Anderson-Higgs mechanism for generating masses in quantum field theory. But in addition to those phase fluctuations, magnons, there can be amplitude fluctuations, like a magnetic moment. I'll show you a picture later. And those are known as Higgs modes or Higgs. Okay, so now this is briefly, I'm getting it from Changa's review article, just to review for you. If I have a free energy, like we learn it in like a ferromagnetism, there is a phase transition from a para to a ferromagnetic phase. And ferromagnetic phase is characterized by this order parameter psi, which has an amplitude and a phase factor. And the free energy is given by a psi squared d psi 4. Now suppose you think of equilibrium, there is no, it's all uniform size over the whole space constant, no time dependence. But in general, this idea has been generalized to time dependent dynamics, time dependent behavior of this order parameter through this sort of effective Schrodinger type equation. Now here is a point I want to emphasize here, because that is what I learned. You can have a Schrodinger type equation where the time is linear and the kinetic energy is quadratic, gradient. Whereas you can also have where the Lorentz invariant one, where the time and the space are the same dimension. So we'll come back to this in a minute. But in equilibrium, there is no time dependence, there is no space gradient. And then we usually do that in our phase transition classes, graduate courses. If A is 0, then the minimum of this, A is positive, the minimum of this is at psi equal to 0, there is no order. Then by some external means, say temperature, but particularly let's say for 0 temperature, we're talking about say quantum phase transitions. I can change A as a function of say pressure, and then when A becomes negative, then of course the minimum shifts. This is classic, and there is a long range order. The amplitude of this is rho 0, which is what we call magnetization, for example, in a ferromagnet. And this phi r can be arbitrary, we just put it equal to 0. So that's the standard going from a paramagnet where psi 0 is 0 to a magnetization M, and you get a phase transition. And that has been one of the beautiful theories of whole phase transitions in there. Now let's go to the dynamics. By the way, there's a very nice paper which I remember when I was, as Surajit mentioned, that I was at Bell Labs very early in 68 to 70. And those were the days of great magnetism in Bell Lab. A lot of new beautiful experiments and crystals were growing. You know, it was one of the most exciting times those days. And I remember Halperin and Hohenberg, I used to hear, I didn't interact with them, they were writing some big paper. And so then I read a little bit of it, then I forgot, because then Chandravarma recently pointed out, you must go back and read their Frisler paper. It's one of the most classic papers in the field of dynamics. So to graduate students who are only reading modern literature, please go back and read those papers. They write beautifully. Anyway, let's come back to dynamics. And we'll be interested mostly in the very long wave, low K dynamics. So this amplitude or the order parameter has some space dependent and time dependent. So that is the amplitude change dynamics. And this is the change in phase. I'll just put delta phi as phi later. Now, if you just go through, and I'll come back later, just I'm giving a qualitative result, if you just solve it, as I told you here, there are two ways of solving it. You use the Schrodinger equation, which is linear, and this, or you Klein-Gauss equation, which is the Lorentz invariant equation. If you do that, what you find very interesting, this Schrodinger dynamics just gives you, say, two linear K. For the Klein-Gordon, turns out one of them is linear, the other one is a Higgs, is a finite amplitude. So I'll come back to this mathematics a little bit. So here we can think about this as, so if you do the Schrodinger type dynamics, you're only getting two modes which are linear, and there is nothing, both are K. One is a phase mode, one is amplitude mode, but they're so much coupled, they're strongly coupled and given K. But when you do the Lorentz invariant one, one gets the balance. So this Chandra Verma, if you look at his paper and also read some of his, that he pointed out this, I'll show you, they pointed out in superconductors. And later he was giving a talk, and in that talk, somewhere he writes in his paper, in the reference section, that he talked with Nambu and he talked with Higgs, apparently, or Higgs referred to that indeed Chandra Verma was right predicting this in the superconductors. Verma and actually Littlewood and Verma. Okay, so now let's go back and check the calculations. So you can do the, so this is the same potential energy, which is so always referred to as Mexican potential. When R is negative, the minimum has come out somewhere here. There is some amplitude motions and the phase motions here. And you can write down the static part of this as a gradient term. And this is just a length scale to make it dimensionless, which is a coherence length in a superconductor. Then they put in two terms. And they do a lot of analysis to find out which is important, which is not, and why it is so. And I'll just summarize the result. If you do a K1 term, which is the Schrodinger one, and the second order term, then you find that you can go back and solve this, and I did. I went through, and it's very nice calculations, but you have to keep the leading order terms and go to the Fourier space. And what you find that here is the amplitude part and the phase part. There's an I here, of course. As you see linear expansion, the leading order term rho 0, I delta phi. So delta phi depends on rho 0 times delta phi is what they call rho 0 times delta phi is this delta phase. PH stands for phase, A for amplitude. So you just go through, then you find a very nice, beautiful result. The amplitude modes and phase modes are coupled. And the coupling is through that IK1, the K1 term, which was the Schrodinger-like time dependence. So then if you can solve it, what you find, suppose you put K2 equal to 0, K2 equal to 0, but the K1 is dominant, non-realistic. It turns out A and phase are strongly coupled, and there is one solution, and that is this linear K. And then they argue that this is what happens in a superfluid, where there is no amplitude modes, there are phase modes, the doubly degenerate. But on the other hand, if you put K1 equal to 0, then they get decoupled, and this is the phase mode, which goes as and amplitude mode. Amplitude mode has a finite energy or finite frequency plus dispersion, and the phase mode, of course, goes to K. So there is a clearly, and this is what they refer to amplitude mode or Higgs mode. So this is the picture. So therefore, the theory and papers by Verma Littlewood went into detailed microscopic understanding of this to show why K1 is nearly zero or so, and they allow for particle hole symmetry. They argue that particle hole symmetry in superconductor in the condensed phase is responsible for this. I'll come back to this. When you do see this in the spin system, I asked Chandra whether there is something underlying. Actually, I also asked Masumoto that in the spin system, is there any underlying particle hole symmetry? Chandra thinks that it is some XY symmetry which is responsible. But I'm still not clear on this issue. Okay, so here is what they calculate, and you can see where is how it's a very simple calculation of those equations. And right at the critical point, they talk about the amplitude modes and the phase modes, the dashed ones. And as you go to the condensed phase, some phase modes remain and the amplitudes. So this is what they are studying as a function of K1, K2, but that's not relevant. But let me summarize here, saying that you need, from this type, their analysis, if your underlying dynamics of the order parameter is linear in time, so you have this phase and amplitude modes get strongly coupled.
Excuse me, may I ask a question?
Sure, sure.
Okay, you talked about time dependence through Schrödinger equation and Klein-Gordon, but you're treating the order parameter, that is condensate, as your main dynamical variable.
Yes.
Then shouldn't it go through dissipative process? Because if you just leave the system alone, then it settles. And
yes,
particles.
Yes, exactly. Now you are absolutely right. There should, and in fact, there's a whole discussion of dissipation in extensive dissipation in Varma's papers, and they, of course, make up life much more harder. And also, if you go and take a look at even for simple magnets, I was reading the paper by Halperin and Hohenberg. They do underlying. They talk about the dynamics and so on, hydrodynamics, but also extensively on dissipation. So what I told you is the basic no dissipation.
Yeah. So then what is the circumstances that you can treat that as some quasi-particle?
Yeah, exactly. Quasi-particles, very weak lifetime, but the real experiments, as you'll see, there are the whole, for example, the amplitude mode decays to two magnons, two bosons, and has a very, depending on the energy scale where they lie, they can be very broad or can have long life. Okay. This is just the Dirac order theory that there is some relationship between the decoupling of the phase and amplitude modes and the dynamics, underlying dynamics which controls it. To be honest, I don't know, is there in the spin system that I'm going to talk about, where you do see amplitude modes and so on, it's easy to see purely from a spin type of picture. Whether there's an underlying dynamics, I don't know.
Okay.
Okay. Yeah.
Good.
Okay. Here is just a quick. This is the paper which excited them. I remember in the 80s, this Surya Kumar and they actually Miles Klein was a seminar speaker in Michigan State. I used to be in charge. And they came and talked about this. And apparently the first explanation of whole thing was the niobium selenide is a 2D type material which goes through superconducting transition. And I don't remember the temperature, but what is important here, they showed, and also by the way, it has a charge density, it's a more complicated system, but there was a new mode which was seen and it was not understood. And Verma and Littlewood wrote two very beautiful papers trying to explain. And this is the one which they referred to at that point as the first observation of Higgs mode. By the way, they did not call it a Higgs mode, if I understand. They later identified this one as the Higgs mode. And okay, so now I want to spend some time telling you about quantum spin systems. By the Bhaskaran, you know. So here, it's very easy. It's a magnet, which has a long-range order. Now, this is the magnetic moment. Normally, if you take this moment, and then if it stays, length remains same, and simply has a phase, and this phase is correlated, that's your magnet. So this is the directional motion or coherent directional fluctuation of the magnons, and they are transverse to the direction of the. So what I'll talk about transverse and longitudinal in this particular case along the direction of the order parameter, magnetic moment in this case, and perpendicular. And in this case, so this is the just direction. Now it's possible, this was pointed out also in a review paper, very long, that for some systems, if the moments are not that hard, they can undergo the amplitude fluctuations. And this is what can be called, so my question, I'm still not sure whether they can be called Higgs modes, but you can see that these days, if you get some good papers in Nature, PRL, the Higgs modes is an attractive name there. So I will therefore call them as amplitude modes, and whether they are Higgs modes in the sense of what I told you about coupling between amplitude and phase, I'm not sure this. Okay, so this is just the qualitative picture of a amplitude mode and a phase mode. Normally, if you look at our ordinary magnets, so Heisenberg magnets, which is very well known, we see the magnons, we detect the magnons, and they play a lot of important role in the physics of the magnetic systems. Amplitude fluctuations are not usually seen. Okay, so now there is when can a quantum spin system have Higgs modes or amplitude modes? We need the longitudinal fluctuation. Remember, I told you about the longitudinal one, which is along the direction that the moment has to be soft, and the transverse moment is rigid, it moves. So it's possible when moment is fluctuating along the length and moving, they can get coupled. But if they can decouple, then we will see them at two separate modes. So first, to have fluctuations, we need the moment to be very soft. If I have a spin half, say copper half spin, very rigid, there is very little chance of it's getting an amplitude mode. So the idea then is look for systems where the moment is soft. So locally, if they can be very quench, we go to zero and develop some finite values, that's a very good system to look for, and which is what I will consider. And also, they talk about a system near a critical point. We're not talking about thermal critical point, but a quantum critical point. If the moment is very soft, and the system is soft, it's possible you can see also those amplitudes. So the example I'm going to use, there is a lot of work where maybe Bhaskaran has done, maybe Affleck, many new papers on this, which I don't know much, where I'm not read. So I'm going to talk about very special system, which is local quenching of spin. And the simplest example is a spin dimer system, which is can have a singlet and a triplet. We'll talk about that in more detail. And I'll tell you about two systems. One is the one which was done by Matsumoto. The other one is what we did experimentally and theoretically at Michigan State, with help from Matsumoto. Okay. Now, this is the summary of, before I get into our models, this is the summary of a statement, what Chandra told me, Verma, and also the paper work by Halperin. Ferromagnets, there's nothing exciting in them. Because the symmetry which is broken is global broken symmetry. It's like rotational symmetry. And there's no Higgs mode, even if it ignores dissipation, as you pointed out, in second order in time equation of motion. I thought having a Landau-Ginzburg type potential, the second order, you will have always a Higgs mode, but apparently they don't. And on the other hand, antiferromagnets of the planar type, XY interactions are stronger than Z. There's a local symmetry breaking, and they are the ones. So somehow this is something which I have to understand in great depth. The Mexican hat potential is not necessary. Having that is not that doesn't guarantee you will have a amplitude mode or the second order pure time dependency. So you need something go deeper. Okay. So now let me tell you about the spin system. This is the simplest system, has been extensively studied, and this is it's not actually completely 2D, but quasi 3D, quasi 3D perhaps. But the main idea of the system is there are these local dimers, two coppers. They interact strongly through these local bonds, and then these dimers interact weakly. So you have to start out with local magnetic units, which are dimers. So dimers spin half, and J is antiferromagnetic. Super exchange has a singlet and a triplet. And in general, they can be degenerate. There can be some symmetry can be there to remove the degeneracy. But the basic physics is, so you have, if the ground, they're all in the singlet, there's no magnetic moment. If the interaction to J prime is very small, basically a bunch of singlets, downstate is nothing interesting. Now you turn on J prime. So once the interaction, so what happened, the interaction between pairs, they start mixing it. So a singlet start getting mixed with the triplet, depending on the symmetry of the interactions. And when you reach a critical J prime, then the system becomes unstable from a paramagnetic state to a long range order state. And now this reminded me many years ago. This is the in thermodynamic phase transition. Is Konstantin here today? No. Surajit? Hello?
Yeah, he's here.
Okay.
But he may be turned. He may
I just wanted to tell him that there's this whole singlet triplet model, blue memory Griffith. They're all exciting stuff in 70s as thermal phase transitions. But now they are coming back as models in the quantum phase transitions.
Yes. I don't know if you can hear us.
Okay, here. So anyway, let me continue. So what you have is that here is an experiment which you apply pressure. What pressure does is basically this is the weaker link. So that starts to get shorter, and this exchange interaction increases interactions. So basically under pressure, what you are doing effectively, tuning this J prime. So increasing pressure, you're increasing the J prime. So very low pressure, the J prime is very small. The system likes to be in the order state with some mixing, quantum mechanical mixing with this, but there is no long range order. But then as you increase the pressure, J prime reaches a critical value. That critical value has been of great interest in exact calculations, and I'll give you some results of mean field theory type. So then the system becomes long range order. There's some antiferromagnetism, and this is the place where they see this excitation. So this is the simplest example of a interacting quantum spin half timers. Okay, so just to see in the physics of that, you can write down the energy, basically this in an effective model where you mix the ground state U with some excited state with some theta phi, and you can write down the effective energy in the mean field like theory, this the singlet energy plus this J minus J effective. J is that same splitting. So J is the exchange splitting of that. If J is very large, that the system basically is, if you think of this, and so J effective is the interaction between them. So if J is very large, J effective is small, then of course, no long range order, V is 0, and you have a singlet. Now you increase the pressure, and which therefore increases the J effective. And as you increase, then you reach a critical value pressure where A is equal to 0. And above that pressure, then this becomes negative. Then you get an order state. So that's the mean field picture of that phase transition from, as a function of pressure, from a singlet to a long range order state. And that's the one, this is for A negative or J factor bigger than J, you have this Mexican hand potential. Okay, so that's the physics of the phase transition in the system. And now if you look at the excitations, this is a qualitative one. I'm going to give you the results. So if you, let's start out with all of them as singlets as a ground state. So now, and then you can flip this dimer, you turn this dimer, flips this one up, this one down, then you get triplets, and you get a triplet-like excitation, which is very simpler to understand, singlet triplet splitting. And there, if an isotropic model, there are three. Then as you below in the ordered phase, I'll summarize what happens. Then you have there is a condensed new state, an antiferromagnetic state, and that has the Goldstone modes and an amplitude mode. And at that critical value, this is the qualitative picture of what happens in this model as a function of the pressure. But I'll show you the results in a minute. Right. Okay, so to do this calculation, this is what was the work of many people have done in this dimer models, starting from Subir, Sachdev, and this is the calculation which was done by Matsumoto, and we extended this to a more complex spin system. So the idea is that you have ith site, that is a single state, and this is a triplet state. Associated with each site, I assign a boson. So they're hardcore bosons. So, but the point is, at this site, I'll have either this or this or this or that. So the total number, there's a big local constraint. And so you write down the effective Hamiltonian, and I'll tell you how, I won't show you this calculation, but I'll show you the more complex calculations. You rewrite the Hamiltonian and then use Bogoliubov transformation and get your, this is where the Bogoliubov transformations are basically linear combinations of these B's, and that's the result. Okay, so don't worry about dispersion. Just at the k equal to 0. This will be, they use 0, 0, 2 pi, but this is the k equal to 0 point here. 2 pi is equivalent to 0. So p less than pc. So here is this point. That's the threefold degenerate one, which is what I showed you here. Because the isotropic model, there will be threefold degenerate. At pc, then this happens, you get all of them become 0. They become soft, and then at P greater than PC, then you get 2 zero energy modes and 1 amplitude. And that's an experiment which, of course, they were trying to, but the real system has a little more anisotropy. I'm going to talk about that. In the disorder state, there is, instead of threefold, there is a splitting due to other local symmetry, lowering of the symmetry. And so that's the first sort of an experimental measurement of these amplitude modes in this dimer system. So let me sort of summarize this dimer result. Then I will, first thing, in the disorder phase, if there's no anisotropy, there are three singlet to triplet excitation, there are threefold degenerate. Now if you apply easy plane anisotropy in XY symmetry, means split up the threefold triplet, two doublets and one singlet which is high in energy, then let's say some reason XY is softer than G, then you will get a splitting, and so between two modes. Otherwise they'll be degenerate. At P equal to PC, if the degenerate, the three went to 0, but the two lower excitation modes become soft, while the higher mode stays gap because there's anisotropy. Then P greater than PC, the order moment appears in the XY plane, and the new ground state appears, new rigidity, new excitations, and this determines the ground and excited states. One of the softened two modes becomes gapped, becomes a longitudinal mode, while the other mode becomes a transverse gapless. So that's what happens in the XY model when the spins are in the plane. So there'll be one angular phase mode, which is single, the Goldstone mode, there'll be an amplitude mode. So that's what happens if you have XY symmetry. And this is what Chandra Verma pointed out, that this is necessary. But if you further apply another anisotropy, both X, Y, Z, then in the XY plane also you have broken the continuous symmetry. Then what happens at PC, again, there will be 3 modes, but 2 of them are gapped coming from, but above PC, then all of them become gapped. The soft mode, which was 0, becomes a gap Higgs mode, and of course the other 2 transfers are no, because of the anisotropy. So if you have small anisotropies in the system, you will see always some gaps. And that's what happens in neutron scattering experiments. Many of the real systems, they're not really, they all have small gaps of millivolts, 2 millivolts, and so on. Typical energy scales are, the J is about 10, 20 millivolts. I'll show you some results of neutron scattering in our experiments, and you will get the energy scale there. Okay, so now I want to, Surajit, I have about 10 minutes.
No, you have more than that. You have
Okay,
about
10
15
okay.
minutes.
So, okay, so here it is. So this is how I got into the system. And I'll tell you a little bit more physics of the system and calculations. So this is a system. They're quasi 2-dimensional. And depending on how you look at it, if you, they instead of copper, they're chromium. And it turns out chromium, this is in the 3+ state, and chromium is a spin 3/2. Orbital angular momentum is quenched, and there's no, it's a 3/2. So these are basically spin 3/2 dimers instead of copper spin 1/2 dimers. Okay, and these dimers, of course, interact with each other. So it turns out, and we got interested in actually I got interested when they showed me the experiments at the low temperature ordered phase. And part of, I've been working a lot in the field with this, trying to compute this exchange couplings in magnetic systems using basic density function, a little bit improved density function theories. But what excited me several years ago when they found that if you think about it a little bit, you can think of, don't see the diamond now. So look at as sheets. So there is a sheet of chromiums. There is another sheet of chromium. These are bilayers, and they're staggered a little bit. This bilayer is here. The second bilayer is shifted by downwards a little bit and sideways. And these bilayers are present. It turns out, if you think of, you take a tellurium compound, chromium tellurium, these bilayers are antiferromagnetic. This is right, and the next nearest is left, right. So basically, this is an antiferromagnetic sheet, and these antiferromagnetic sheets get coupled through these dimer interactions. They are antiferromagnetic. So that's the ordering here, and here you see that if you just switch this to that, immediately these planes become also. So they are ferromagnetic sheets coupled anti. So overall, the system is antiferromagnet, but if you're looking at 2D orderings, these are ferromagnetic sheets antiparallel to each other, antiferromagnetic sheets antiparallel to each other. So that first excited me. Before they did this, they did substitute measurements, and we wanted to understand, and we did. In the end, try to understand the physics of this, why this interaction is ferro, this is antiferro, but that's a different story. I won't tell you. But now I will talk about the dynamics. So happens this can be thought of another way, that this is the dimers are strongly coupled. J1 is the coupling constant. These interdimers, depending on whether you are this or that, can be ferro or antiferro. So that's a little simpler model to write down the Hamiltonian dimers interacting with each other through either a ferro or antiferro. And these interactions, long range, are weak, finite to explain quantitatively the experiment. Okay, so the system can be thought about quantum dimers interacting with weak interdimer interactions, which can be ferro or antiferro. Final dynamics will not be very sensitive, I'll tell you. Okay, so here's the experiment. And that's what we started, after we understood the exchange, so on. So this is a typical neutron scattering experiment in the ordered phase, energy versus Q. And you find the excitations, and the lower ones are magnon-like, but there's always something here, there's something up there. And similarly in tellurium, this was sort of the low energy up to this. There's something up there which was not, yeah. So what we try to do first, so let's try to, okay, now the experimental is, of course, you can do the intensity versus energy for a fixed Q. And this is a very interesting experiment. You can, result, you can see that in the disordered phase, there's one big bump at about 7 millivolts. And then as you go to the order state in this tungsten system, then you get a transverse and a longitudinal mode. So there's already some evidence of an amplitude mode in this system. And this one is for a different Q range now. So this is trying to filter out this, trying to fit this data to something a little bit more. I have to understand this one, I forgot this one. For the tellurium, things are a little bit more complex. There's some evidence, and they did some filtering to see that there is some high energy mode here. Okay. So experimental neutron, inelastic neutron scattering does tell you that you see some low energy modes, and above that there is something. So the question was, what is that? So that was the, so what we did, okay, so this was the calculation which was done in collaboration with this, as I told you. So we'll have dimers, and the dimers have to interact with each other. Now, there are two ways of doing excitation calculations. I'll show you here. So the one which is more realistic to keep all the dimer physics is to take this as a unit. So all this J is a dominant term. So this is the dimer, intradimer is the interdimer. And this intradimer has this J1, which is the, and this is a little more complicated system. So it's math is, this I is the same side, mu L, mu R. So L and R are the two components of the dimer. And by the way, we had to do it, I was trying to write up and down, but that got confused. So Matsumoto said, make it left and right. Think of this as left and right, left and right. So there's just a nomenclature. Okay, so J1 is antiferromagnetic, strong antiferromagnetism. This J2 can be either small antiferro or ferro, and J3 is small, forget about that. So you take this, you can solve this problem, a little bit more complicated, but so we did 3 calculations, we're going to show you here, ground state, and see whether this system has that phase transition from a quantum dimer to an order state. First one, basically a mean field like. Then we looked at the excitations, 2 types of calculations. Linear spin wave theory, which fixes the moment, so there's no amplitude fluctuations, and clearly no longitudinal fluctuations, only magnons. We see how that compares with experiment. Then we extended the theory to allow for this longitudinal fluctuations and see how that compares to experiment. Okay, so first let's look at the ground state first. Let me go back here. So is it the standard mean field type theory? There'll be say J, Ij, Sij, you average, and you calculate the average as a function of parameter and so on. Here, the things are a little more complicated. So here a little bit, so bear with me. This is what is that you break them into 2 sublattices, just like we knew it's antiferromagnet, A and B. So that A will have left and right. That's the intradimer. And this is the interaction between, this is the field, forget about that. This is the interaction between the one left with the A, say, let's call it A, this is B. So this interacts with the B of the right. So this is the interaction up with the down of that. So you can similarly right of that interaction, left of this, and write it down. So effectively, we have a Hamiltonian, which then has to be solved. So if you think of this one, so this has what? There's a 3½ and 3½. It's 16 states. So essentially, this is a 16-state quantum system. So this mean field. So what we do is to do a 16 by 16 matrix, compute the average, do self-consistently. So it's what is a little bit of a computation problem, but Matsumoto did. He is very good in that. So we solved that problem. And so here is the result. Forget for the time being on this. So for the weak interdimer interactions, J2 is very small, then this is, of course, a disordered phase. No, this is like your paramagnetic or disordered phase. Then when you reach a critical value of the interaction, then the magnetization goes here. So that's the phase transition point, and a mean field theory gives you some number like this. And this is where we try to compare with actual experiments and to get some numbers so that we can then numerically compare with the inelastic neutron scattering. So this is, I'll come back to these different modes later, but this simply is, this figure shows that as you increase the inter-dimer coupling, then you get a phase transition. Now here is a point I want to mention. In fact, if we have a paper published in Physics Data, I would like you to take a look at it. The title of that paper is Seeing Amplitude Fluctuations Far Away from the Critical Point. Now, there was a lot of not folklore, but discussion that only if you are very close to the critical point, then the system is very floppy. And this is where you should be able to see the fluctuations. And so one of our main conclusion of our work is that you don't have to come close, you can be far off, and yet you can see, but the underlying physics is that your quantum spin-half systems won't show it. Spin 3½ because of the larger these matrix elements and so on, you can see them in neutron scattering. And those of you who have some interest, I would strongly request you to take a look at our supplementary where we work those all of them out.
May I ask a question?
Yes, sir.
In the previous slide, it looked like it's just a mean field theory. Where is the quantum element?
Quantum element, these are quantum operators.
Okay.
These are all quantum operators. So what you do is you write down this in the basis of, it's a 16 states for this and 16 for that. You write down the matrix, it's a 16 by 16 matrix. And in that matrix, you diagonalize and you compute the averages. So,
okay.
so this is a fully quantum mechanical 3½ spin operator.
But you have a mean field value like
Exactly, it's a mean field as far as, but the mean averages are computed in the full spectrum of dimer states.
Right, you have a quantum critical point. I mean, I would say classical mean field theory.
Well, mean field, you can do t equals 0, still you do mean field theory, but you keep the local quantum mechanics as best as possible. Okay. So dimers are treated as fully quantum mechanical.
So that's why the phase transition line, dimer and an antiferromagnet, they simultaneously go to 0.
Yeah, exactly, you're right. So the phase transition tries between when this coupling is very weak. We know when coupling is 0, it's basically a bunch of quantum dimers.
Okay.
So that's
classical mean field theory wouldn't give you that.
No, mean field theory, no. If there's no interaction, your mean field theory simply there's no interaction. The mean field theory is no, there's no mean field. So basically, we have a bunch of non-interacting quantum spin 3½ dimers. They will, as you know, if there is a J, they're antiferromagnetic. There'll be singlet, ground states, triplet, quantet, and so on. So okay. Those will be the states of the system. And now, when you increase the interaction, just like that singlet triplet, the singlet and triplet get mixed. Here also the singlet, which is and triplet get mixed, just like in the spin-half system. And then the downstate becomes a mixed state, which then develops along the job.
Okay, maybe this is a different question, maybe unrelated to this. Previously, you said Higgs mode going gapless. Is that associated with the excitation of a triplet?
Yes, here, okay, let's explain very simply physics. So let's say no interaction, then we have a bunch of a singlet and triplet, and of course there'll be other higher energy excitations, we have dropped it. The leading order is the singlet to triplet. But now as you put in the J interaction, J2, then that triplet starts to come down. Some of them splits, so then they become soft. So that's what happens. Interaction does affect. There's no long range order, but the interaction does reduce the energy spectrum of the diver.
Okay.
Like a field. If you think of a field, oh, okay, there's a very simple analogy. You take it no interaction, just apply external field, then that will split the triplet, and one of the energies might come. But here it turns out all three come down. Because the
Bhanu, if I may make a comment.
Yeah, Bhaskar, yeah.
So some people call it as triplon condensation.
Okay, yeah, okay, yes, sorry, I should, okay, tell me a little more. Because there's a triplet, then coming down to 0, so they condense and become a triplon. But there is a mixing between a singlet and also triplet. Well, triplon is a linear combination of singlet and a triplet, one member of the triplet.
That's right, yeah.
Now, a triplon is a complex object, which is a singlet, triplet, singlet and the whole triplet mixing. Am I right? Okay. Is that okay? Can I go?
Thank you.
Yeah, go ahead.
Please go ahead.
Okay. Okay, so here is what I want to show you, what happens. So suppose you go to this order state, and you know the ordering, and you just calculate the standard spin wave theory, which is very well known. You take the moment of the chromium is fixed, no dimer states, nothing. You make them order, fix them, and do the standard spin wave calculation going through Bogoliubov field. What you find, magnons, which is very simple. But and that is explains very nicely these low energy ones. That's what we did first before we start. So it turns out simple magnon type calculation where the chromium moments are fixed, you can parameterize and fit to this one. I'll show you a better picture later. So the low energy part, this going to 0, and this flat portion, they were all could be understood within the so-called simple linear spin wave theory, which in real order, you assume that all chromium moments are 3/2 order, and each one is fluctuating, but there's a coupling between them, and you can. So the linear spin wave theory cannot account for this stuff here. So you can see clearly, this is the experiment, this is the linear spin wave theory. Clearly, this mode is basic. Similarly, the linear spin wave theory is here, experiment here. That's pretty not bad, but these are all absent here. So there's some. So and also, I just don't want to mention here. There's this shifting the sign of why the J2 switches sign and large is some interesting quantum chemical physics, but let's not get into there. So now let's go to the better theory. Okay, so now, so this is, let me come back to this here. This is the theory which was done by Matsumoto for the simple singlet triplet system. So now that has to be extended with the ordinary spin half systems. So it had to be done for the spin 3/2. But still, it turns out the singlet triplet are the dominant mixing. So so we computed this dynamic structure factor to the spin-spin correlation function, which the neutron scattering measures. So you can clearly see the experiment here. This is the low energy. This is that intensity above that. Nothing here in the spin wave, linear spin wave theory, and shows up beautifully in that one. Similarly, for the here, this here. Now we don't see it, and here there is the problem which we still don't understand, and that relates to one of your an earlier question about the lifetimes and dynamics and dissipations and so on. But the linear this type extended spin theory, which allows for this amplitude mode fluctuation, gives you beautifully. But the point is, it broadens out very, in which we don't really understand the lifetimes of this amplitude modes.
Another 5 minutes or so.
Okay, yeah, I will be slowly coming down.
Okay.
So let me summarize this part of the calculations. So what I want to tell you that transverse and longitudinal elastic spectra of this. So you see here, this is the transverse modes, and these are multi-magnon contributions, which and then clearly there is this amplitude mode, or if you want to call Higgs mode, which shows up very nicely in the extended spin wave theory, which keeps the amplitude fluctuations using the singlet and triplet excitations of the time. One of the things which I wanted to mention here, you see a large intensity here, both is partly the intensity of these lines depend on matrix elements of the spin operators, and this 3-half, as some of you in our graduate courses we learn, spin half, spin 3-half, Wigner 3J symbols, Krebs-Gordon coefficients, they enhance this matrix elements by a factor of 20 or something. That's details are in our paper. Okay, so now let me 5 minutes. I'll just tell 4 minutes. This is something which I'm reading, and I like it. This is 2 very interesting papers, and this apparently has been Bhaskar, and you know a lot about this. The Ruthenates, and I do hear about Ruthenates in seminars, and one of my, so apparently Ruthenates, there are 2 papers which have come out really pushing, I mean, they simply write Higgs modes. The Ruthenates are some, these are compounds where the magnetic atoms are the rutheniums. It's a 4+, ruthenium 4+, if you do the chemistry calculation, 2+ calcium 4, 8, ruthenium 4+, turns out ruthenium L is equal to 2, S is equal to 2, and the spin orbit is very strong. So spin orbit interactions lead to, L, as you know from atomic physics, L minus S, L plus S, 0 to 4, and the ground state is a singlet depending on the filling and sign of spin orbit coupling. So this is another system, but these are not spin singlets. They call it spin orbital singlets or mixed singlets. A lot of fancy spin orbital entangled singlets, you know, all fancy names you can use. But from atomic physics, they're simply J equal to 0 and J equal to 1. And therefore, they would have a singlet and triplets. So the physics maps onto, again, a singlet triplet model of a quantum spin dimer. But there are no dimers, they're single. So they again interact with each other. But there are some interesting stuff here which may be of that there is a large tetragonal distortion that breaks the symmetry. So the triplet is no longer 3-fold degenerate, but breaks up in the singlet and the doublet. And then there is a very, very small orthorhombic symmetry breaking also. The so-called, if I think of this as A-axis, B-axis, and C-axis, the small monoclinic distortion, there is a small orthorhombic distortion. That again splits the degeneracy in the plane. The XY plane is not perfectly isotropic. But again, what Professor Bhaskaran mentioned in the singlet triplet system condensation of triplons, here they call it condensation of spin orbit excitons. You excite locally from a singlet to a triplet, but these are spin orbit split states, so they call it spin orbit state excitons. In the absence of interactions, they are locally excited, and in the presence of interactions, they interact and they condense into D. Okay, so you can therefore construct effective models, and these are 2 beautiful. So there is one thing which I am reading, trying to understand. Neutron scattering is a messy experiment. There are 2 very nice papers by Professor Keimer from Max Planck. They wrote one paper in Nature Physics. I think they have neutron scattering here, and this was Raman scattering with some theoretical modeling. And the basic idea again is the order as antiferromagnetic. I wish there is a system which ordered ferromagnetically, so which then, if we are all right, we'll just see the singlet only in the disorder phase with excitations, and the ferromagnetic phase we should not see any of this amplitude modes. Then what they find, of course, what this paper, this is a later paper, is a Raman scattering paper, and this is a neutron scattering paper. And they strongly find, and these are some many calculations. I'm just showing you the paper, the splitting orthodromic symmetry pushes this up. So the leading order is really S and XY type model, but there is some small local orthodromic distortion and some additional interactions. So therefore, this also splits. So there is always, finally, there are gaps in the spectrum. There's no gapless modes, but they could clearly explain the amplitude modes by one symmetry in Raman scattering and the phase modes by another symmetry. And they do see both the BG channel and AG channel. And this they identified clearly as the amplitude mode, which was not seen here. So this is a clear, so you can see the title is purely fully into Higgs mode description here. Okay, so I hopefully maybe some of you who can study this paper and this maybe give us a more, the actual theory is not very hard, an effective XY model with anisotropic, and it can be solved, it can be understood. But I'm still working on that paper. So let me, I think time is up. So my summary here, we will see in the spin models, the dimers or the spin orbital models, amplitude modes are easy to see or are possible. So I still have not understood if I took the spin orbital model, singlet triplet model, do the ferromagnetic coupling and calculate neutron scattering, how the amplitude mode goes away. I don't know the answer to that question. I'm still thinking about. I hope some of you know and can help me explain that one. Then the other question is also, is there always an underlying dynamics which satisfy Lorentz equation for amplitude modes in spin systems? Is there any particle Hole symmetry effective theory, which I don't know. I wrote an email to Matsumoto. So he essentially told me that he doesn't understand if there is any underlying particle Hole type symmetry, but purely from spin models, we can understand how applying some orthodromic distortion, cubic distortions, tetragonal distortions, orthodromic distortion, we can break the symmetry and see which modes comes where. That's we can understand in our models. But I don't, is there any underlying theory which has particle Hole symmetry for the spins? I don't know. The other issue which has bothered, and some referees were very critical, that the 2 Magnon spectrum, because when you see something higher in energy than the single Magnons, so what's happening to them? Are they there, or are we misidentifying the experiment by this? That's still an open question. And then the third one is, of course, your damping issues. And we are thinking about it. And as you know that now I'm isolated here, I don't do any calculations. Slowly I do, but interactions are not easy these days. But we're still thinking about. We'll see what happens. Let me see if I have. Okay, here I just give you these references. This is the reference of Pecker and Verma, which the first couple of chapters I did very carefully. These are the 2 experiments on Ruthenates, which still are really, to me, are very interesting recent papers worth understanding all in detail. They've understood some, but I'm not sure everything. Then this is the paper we wrote on this physical research on this quantum spin 3-half dimers. And this is the one by Matsumoto on the spin half. So these are essentially the papers which I discussed, referred to and discussed. Okay, so let me go to here. That's all. This is my, thank you very much. I hope you got something out of this talk, and we can ask questions.
Yeah, so let's first thank Professor Mahanti. You have to unmute yourself so we can give him an applause. So please ask questions. I think this was a very exciting subject, so I'm sure there'll be questions.
I have a question.
Yes, please.
Yeah. Okay. So, if you're talking about two-dimensional XY model after this condensed state, it allows for vortex pair excitations, vortex anti-vortex. It turns out in some nonlinear sigma model, their energies are not very large. So I wonder, because you showed the neutron scattering experiment and showed some flat region and pointed it out that it's a multi-magnon contribution. So at least according to some model, they could correspond to vortex pair excitations, bound vortex, anti-vortex pair. So am I clear?
Is it Bhaskaran?
Yeah.
Bhaskaran, can you, no, so tell, no, I can't hear because I'm using my hearing aid, but can you repeat it please again, little bit louder?
Yeah. So I'm saying that since you are talking about two-dimensional XY model effectively, so there are non-spin wave excitations, namely.
Yeah. Okay, I get it. Okay.
So their energies are not very large, it turns out. They are like twice the spin wave bandwidth. So I wonder if the neutron scattering data that you just pointed out, you said there is a flat portion which is a multi-magnon contribution.
Okay, yeah, I get it. Okay, so let me sort of rephrase. So yes, if of course, as we know, a strictly XY model, we have all the spin excitations are completely different, right?
Yeah.
So now what you are saying, so let's say I have a XY anisotropy. That means say G interaction is still strong. So it's so long range order perhaps in the plane, but there will be excitations of peculiar to the XY model, which will be like a topology of vertex excitations. So, okay, so that's a good. Bhaskaran, that's a beautiful question. I don't think, of course, spin wave theory, even extended spin wave theory, do not capture those states. I'm sure. So,
there are some work where you can go to nonlinear sigma model and look for like solution.
Oh, that's a very good. So okay, that's good. So the question then is, I can I can take an anisotropic model, XY with a small g anisotropy. Then the question will be that what happens to well, first thing, what is the nature of those excitations because of the anisotropy? Because in the strict limit of infinite anisotropy to be purely those excitations which you are telling. Now I have still a GG component. Yeah, I don't know. Maybe I have no idea. I have no idea. Is there a calculation one can do and find out what they are as a function of the anisotropy?
Yeah, there exists some old we can correspond. I will send you.
Oh yeah. That's a good. Maybe I mean they are, but this could be also true for the Ruthenates too, because they're also the same.
Exactly. Yeah, right. In fact, Ruthenates are very fascinating because, in principle, if you apply pressure to calcium Ru2O4, it is like strontium ruthenate, which is a P-wave superconductor. So it is teaching us something about your analysis or all this triplon physics. It's teaching something about the P-wave superconductivity, because you reach that superconducting state essentially by pressure when you go from calcium to ruthenium system, because
Okay.
ionic radius changes, chemical pressure is changing. Sorry, we can discuss it later.
Okay,
No,
I'm
this
going
is
to try.
fascinating.
Okay, I'll write to you. I'll send you. Yeah, that's yeah, possible. This is an interesting, very interesting one. And how do you see them also in the neutron scattering experiments?
Yeah, thank you.
Okay.
Thank you.
Yeah, thanks, sir.
Now, when you introduce the Klein-Gordon
Dynamics.
equation for dynamics and pulled up nonlinearity in an obvious way, because Klein-Gordon is a standard nonlinear equation, right? So
Just a second. So is it no? I mean, just a second. I mean, time one just but it's because there's a mass term. I just it was Dirac, of course, is Lorentz invariant with linear time and linear space, right? Delta. So the Klein-Gordon is the old Schrodinger equation, second order in space, the del square term, and del square. So there is no the potential. There is no psi. There's no nonlinearity. It's still a linear Schrodinger equation.
Okay.
Yeah. Just the whole idea is in a way that if you put that term delta t squared, and this you can easily see that in order they decouple, the phase and amplitude decouple.
Right. Okay, I see.
And Chandra's point was that Higgs, because when he worked out the theory, he was using a Lorentz invariant theory. I don't think he used the Klein-Gordon, but Lorentz invariant theory, he claims, therefore, the decoupling of the amplitude and phase mode is inherently due to Lorentz invariance. And that's his story for the
That's a fascinating, that's a fascinating angle to explore. And I was just thinking that amplitude fluctuations, actually, if you take an interacting many particle system, but the interaction has nonlinearity. That's why the nonlinearity was bouncing in my head. Then it is almost guaranteed that you will have amplitude fluctuations.
You're right. All your nonlinear equations are solitons are amplitude modes.
Even localized excitations, nonlinear localized excitations, can manifest themselves as amplitude fluctuations. In fact, they probably almost necessarily do. So while in the mean field picture, there are advantages of understanding things in an organized way if some form of interaction is turned on. So if it is like a little bit beyond mean field.
But beyond mean field, the one which you see these propagating modes in the actual calculation of the extended mean fields, you see those amplitude modes coherently propagating with as a function of q, and leading on there's no lifetime. They have a mass gap. There is dispersion. You see very nicely all. Is that because they are coherent amplitude? Like, by the way, you can think about yours. I think in the soliton picture, soliton is excited but coherently propagating from one left to the right.
Right.
But without decaying.
Right, and many of these systems are pretty robust in the sense that even if you add some amount of disorder, which is almost necessarily present in all experimental systems, they probably wouldn't even notice any of it. So these can be robust against disorder also. So the role of disorder may be an interesting issue to learn about. I don't know if it's been done.
No, not in the. You are saying that effect of spin, say exchange is disordered a little bit. There's some randomness in exchange.
Right.
Or whether or the single triplet locally extra distortions.
There are weak glossy effects. Some level of glossy effects might be. I mean, So the Higgs modes may even survive those, is what I'm saying. So it may be quite robust.
Excepting, yeah, that's true. But some cases, clearly the lifetime of these ones, magnons or Higgs amplitude modes, even with this extended spin wave which Matsumoto did, they are not there. So you have to go beyond, even just like even in a simple magnon lifetime, even if no amplitude mode, we know we have to go beyond linear spin wave magnon interaction to pick up the lifetime. So you have to go to higher order. Yes, I mean, even I think I didn't read it, but Chandra Verma in his later part of the paper, when he derives the microscopic theory for this, does talk about the lifetime of those amplitude modes. But in the spin systems, I don't know though. I don't know yet. That's my lack of understanding literature. There may be if I can Google, find out the lifetime of amplitude modes, and because it's pretty broad. Experimentally, they're not narrow. There's a lot of, yeah, but excepting they're isolated. When they're isolated from the other, then they can be seen.
Yeah. Okay, sorry, I asked too many questions. Yeah, please go ahead.
I want to make a comment about Surjit's comment on solitons. In fact, if you think about nonlinear sigma model, with SU2 symmetry, you have topological soliton, namely skyrmions. Now, if you introduce XY anisotropy, the skyrmion becomes a vertex-anti-vertex pair. So they are deeply connected actually. These are all solitons. And it turns out these energies are comparable to the spin wave bandwidth. So I have some paper, I can send it to you. We can discuss in detail.
Oh yeah, I'd love it.
Topological solitons. In the context of helium-4 and also interacting bosons, some of these things are related to dark solitons and various amplitude solitons issues. Because one can ask similar question for superfluid helium-4 also, because you have a phase fluctuation and what is the corresponding Higgs mode. So,
Bhaskar, tell me, helium-4 can have or does have Higgs-like modes?
Yeah. So if we take this analogy further, for helium-4, you have a Gauss-Petevsky equation, which is like nonlinear Schrodinger equation for superconductor.
Okay.
So the scales may be different for helium-4, but as a matter of principle, it does exist there. It may have lifetime, but we know that there are solitons.
Yes.
In the corresponding interacting boson systems.
Yeah, there's been quite a bit of work done on these systems.
Okay, here's a question. So the solitons can be thought about. They're certainly clearly amplitude modes.
But then it has a topological character also. In addition, it has a topological character.
Whereas Higgs particles, Higgs modes do not have topological character.
Exactly. Yeah.
Right. Okay. So the solitons are more exciting then. Eh?
More exciting. Incidentally, Peter Higgs, in his later part of life, worked on solitons.
I see.
One of our Indian colleagues, Professor Lakshmanan from Trichy, he was his postdoc, working on solitons.
I see. Good. Straight.
Yeah, it would be lovely to have him here actually for a